Good evening, everyone. So I welcome you all to this institute lecture, which is happening as part of lecture series, Science and Beyond, being organized by British Council and Indian Institute of Science Education Research, Pune. So before introducing the speaker, I request Nidhi to present a bouquet to our speaker, Professor Iain Stewart. I request Kalyani to present a bouquet to today's chief guest, Professor Sandeep Singh, Dean, Alumni and International Relations. Okay, so it is really my pleasure to introduce today's speaker, Professor Iain Stewart, a Scottish geologist, a fellow of the Geological Society of London, and president of the Royal Scottish Geographical Society. He is professor of Geoscience Communication at the University of Plymouth and also a member of the scientific board of UNESCO's International Geoscience Program. Described as geologist rock star, and after saying, I can say, looking wise also, a rock star. He looks like a rock star. So, Professor Stewart is best known to the public as the presenter of a number of science programs for the BBC, including the BAFTA nominated Earth, the Power of the Planet. His main research interests are in the broad area of earth hazards and natural disasters, particularly the terms of identifying past major earthquakes, tsunamis, and volcanic eruptions in the Mediterranean region. In 2010, Stewart was recognized by the Royal Geographical Society for popularizing geography and earth sciences. He was appointed member of the Order of the British Empire in the 2013 birthday honors for services to geology and science communication. In 2013, Stewart was the recipient of Athelstan Philhouse Award by the American Geophysical Union. So with this brief introduction, I request Professor Stewart to deliver his lecture. Please welcome Professor Stewart.
Thank you very much. It's a pleasure to be here with you today. So I've got two heads on. I've got one head, but I normally have two heads. One of my heads is a geologist, and the other is a kind of communicator with the public. And today I'm going to speak to you more with my geology head on, but I'm going to mention a little bit about some of the communication work. So my fundamental interest in talking to you today is to talk about the paradox that we have as a geoscientist. How many people in the audience are earth science or geology? Earth science. Whoa, a lot of people. So what other disciplines do we have in here? Do we have any chemists in here? No, chemists. Physics? Any physics? Okay. Engineering? Okay. Oh, okay. All along the back, the engineers. Okay. So this is kind of for everyone because many of the aspects I think I'll talk about are translatable into other sciences, but I'm going to mainly talk in the geoscience. So the engineers will have to kind of work through what's relevant for them. And really this slide just shows the key problem I think we have in geoscience, which is that we're kind of schizophrenic. We've got two worlds to us. The top one is that we understand the planet. Our interest is in the deep physiology of the planet, how it works and what it means for us. So we understand the rhythms of the planet and all the rest of it, its feedback loops, etc. So it's kind of like if you care about the planet, then trust the geologists. They know how the planet is. They know its health and well-being. But then there's this side of geology, which is the side that finds stuff, mineral. This is a gold mine in Australia, finds stuff, oil and gas. And many of those aspects are the very aspects that are a problem for the planet through things like climate change or environmental kind of pollution and contamination. So this case here is we're the problem. Geologists are the problem. And so, but at the same time, this is producing things that's useful for society, that society needs. So I'll come back to this again later on, but the role of geoscientists in the big picture of how we build a sustainable future for the planet seems to be really important. It was mentioned that that I've done television, and I've got another talk that talks all about the kind of popular television, but essentially this was just to show that from 2004 onwards, I've mainly been working with BBC Science, trying to get programs, trying to raise the profile of geology, geoscience, earth science, whatever we call it, to the general public. So I thought I'd show a small clip, video clip, to show the style of the program, because it is quite popular. And let me just show you what that's going to be like.
The discovery of Africa's deepest origins started with Livingstone's fateful expedition 150 years ago. As he made his way down the Zambezi River, Livingstone found his progress suddenly interrupted by a strange sight. A huge curtain of mist rising up from the river ahead, accompanied by a steadily increasing roar. Leaving his team behind for fear of putting them in danger, the explorer continued his journey on foot, only to find his way blocked by the most impenetrable of all obstacles. Known to the locals as Mosio Tunya, the smoke that thunders.
We, of course, know it as the Victoria Falls.
And the ultimate way to experience the falls involves getting your feet wet.
This is the way to see the Victoria Falls. Oh my gosh.
While the water around me cascades down more than 100 meters to the river below, this pool forms a hidden sanctuary.
Okay, so that's not a very normal thing to do for a proper academic professor. So I should explain a little bit about my background. So I am a proper academic professor in the sense that I did an undergraduate degree, geography, geology. I did a PhD on earthquake geology. And then I really spent about 12 years studying earthquakes, tsunamis, etc., in the Mediterranean region. And then 2002, I kind of left my academic job to try to get television going and start television, and then came back into academia in about 2004 at Plymouth University, where I am now. So the last, 10 years, 11 years, I've been juggling proper academic research with popular communication of what I do. So it's a rather strange balancing act. And really, I want to talk today a little bit about that, the academic side. And my basic question or issue I have comes out in this quote by Mora, talking about the need for geologists and sustainable development. It says, although a larger involvement of geologists in sustainability issues is critical to address complex human environmental systems, our representation is slim in relation to other scientific disciplines. what that is really getting at is that sustainability is with this big issue that lots of people are talking about. But actually, very few geologists are involved in it. And sustainability or geology doesn't feature very heavily in the discourses, the conversations about sustainability. Geology is seen as a very narrow, marginalized aspect of sustainability. And that's a little bit odd because if you go back to the earliest, the kind of seminal study that sets up geology, which is James Hutton's theory of the Earth in 1788, 150 or so years before. He's famous for lots of lines, but this is the line that is very early on in that study. This globe of the Earth is a habitable world, and on its fitness for this purpose, our sense of wisdom in its formation must depend. For James Hutton, understanding the Earth had really one purpose, and that was to make sure we maintained the Earth as a habitable planet for life and ultimately for us. So it's the sustainability and the health and well-being of our planet occurs right at the heart of the basic tenets of our subject 200-odd years ago. And there's a whole set of reasons why we could argue that geology, geoscience, earth science is important for sustainability. Minerals, most of the stuff we get for our gadgets, our computers, our modern way of life, come from things dug up from the earth and found by geologists. Likewise, much of the energy that we've relied on thus far, particularly through fossil fuels or nuclear, through uranium, comes from things dug up or sucked out of the earth. Now, this is changing, and we're moving towards a low-carbon world. But high carbon will still be there, and some of the new technologies are going to demand new materials. So solar, for example, demanding new components, that rare earths that will require mining of new things. Building our cities, sustainable cities, the infrastructure that we build, the engineering of that will require geoscience knowledge about earth materials and properties. The land, the soil that is required for agriculture, the fertility of that is intrinsically a geological aspect about where elements and nutrients are coming from. And then water, right in the middle, because really it is the centerpiece. Whether it's monsoonal systems in India, whether it's delivered from the glacial Himalaya, water is a fundamental, crucial element. And again, geoscientists have a big role in understanding that. And of course, I guess the spectre in all climate change, how a changing global climate and a changing local climate will affect that. Health, many of these aspects up here, as I said, have a detrimental aspect. And so how do we do all of this? And actually, how do we make sure that we're not polluting overly our environment? So we need, in terms of the health aspects of the geology that we do, and actually also the positive benefits of geology too for health. And also natural heritage. We talk a lot about cultural heritage, but I'm involved in the geoparks, and geotourism is a big thing. Actually, this is something that can bring in money. And finally, the one I'll talk most about, hazards. The fact that the sustainability of our world is hampered and inhibited by natural catastrophes that hit our kind of populations. So it's almost every geological organization will have a fact in it that talks about how important geoscience is for the world. This is the one I've taken from the Geological Survey of India. An understanding of the Earth and its geological history is the key to an ecologically sustainable development of the planet's resources. So geologists themselves feel that they're fundamental to this issue of sustainability. There's several reasons for this. One is that geology gives a truly planetary perspective about the planet. We live on the most incredible recycled planet. It's been around for 4.5 billion years. At least 3 billion years has had life. And through that time, an active, dynamic planet has essentially maintained the conditions required for a habitable planet. So we have a heat engine that drives an outer shell where we get new crust developed here in the ocean ridges. And then we have a kind of conveyor belt system that carries that crust and then pushes it down at what we call subduction zones. And this whole thing gets recycled. And that recycling process recycles elements and minerals. It recycles water. So the water that we have now is probably the same amount of water we had 4 billion years ago. We've managed to maintain it. So the Earth itself is an amazing, sustainable system. And therefore, geologists studying this can bring some of that big scale picture to part. There's also a kind of intellectual framework about studying it. The planet perspective. This top one here, that's the atmosphere that we've got. So if you take the atmosphere, you strip it off in terms of what we use to breathe, and you have it as a ball of air, that's essentially what we have. And it's tiny. And so in comparison to when we talk about polluting the atmosphere, we're talking about polluting, that's what we rely on for our life support system. And likewise, that is all the water that we have. You strip all of the oceans and the ice caps, etc., from the world and hang it as a droplet on the planet, that's it. So when we talk about, the polluting the oceans or changing the acidity of the oceans, it's actually a comparatively small amount of volume of material we're talking about. And geology, because we have that Earth focus, allows us to see things in a slightly different way. The other second aspect that I'd like to mention is that the toolkit, the skills toolkit that we have in geology makes it very appropriate, I think, for looking at issues like sustainability. The first thing is that geologists aren't normal. We're strange. We think differently to other scientists. I can see all the engineers going, yes, they do, and I can see the geologists going, yes, we do. But what do I mean by that? So if you look at the range of the collection of skills that go together to make a geoscientist and earth scientist, they are different to they overlap with other things. But several. We have a strange relationship with time. Our currency is to talk about millions of years or hundreds of millions of years. And for a long time, that's been a problem for us because that's set us apart from every other normal person. We intuitively deal with a complex system, and increasingly with Earth system science, we recognize that there's the lithosphere, the so-called solid Earth, and that interacts with the hydrosphere, the cryosphere, ice. It interacts with the atmosphere, and it interacts, of course, with biosphere. And so we're dealing with these complicated systems all the time. The other thing is that we work in the field on relatively small-scale features, but what we're interested in is taking it to that big planetary perspective. And therefore, we really cross a whole wide range of spatial scales. And we also think in 3 dimensions. And that may seem obvious, but actually very few people think about what actually lies beneath their feet. More than a few meters of soil, people have a very blank view of what's down there. And yet what's down there is our world, and we deal with that, we feel very familiar with it. So the collection of those skills makes an earth scientist different from any other scientist. And all those other sciences could define themselves in different ways too. But the point is that I think that many of the issues that I'm going to talk about fit quite nicely with sustainability. The first thing is that geology is an interpretive science. So, so here's me. I'm studying this particular rock with a hand lens down there, and I am interpreting what I see. I'm seeing certain minerals, and I'm trying to work out not just what the minerals are, that's the easy bit, but what that means. So in a way, geology has got far more in common with an obscure field called hermeneutics, which is the art and science of interpreting ancient texts, but it was started on the Bible. In other words, looking at words, you know what the word is, but that's not enough. You need to know what the context of the word is. Who was speaking at what particular time, and how did they use that word? So it's the same thing for me. I'm maybe looking at some minerals, but I'm trying to think, what was the environment? So this happens to be a desert sandstone in the Grand Canyon, and I'm going back maybe 250 million years when this was like a Sahara-type desert from the detail that I'm looking at. Now that means various things. Is that we look at objectively what is there, like every other scientist, but we also bring to bear a whole set of presuppositions and expectations that are culturally determined. In our training, we put these things together. The point I want to make, to highlight, is that what that means is that it's got a high level of subjectivity. And we, for a long time, geologists have been very embarrassed by this subjectivity. And we've kind of looked up to the main sciences like physics and chemistry. We've gone, oh, I'm very sorry that we're not as good as you because we are subjective. And there may be some truth there, but the point is for sustainability, where there's a huge amount of subjectivity, that actually places us in a good position because we have to deal with this limitation constantly. Let me give you an example of subjectivity in the real world of geology. One of the big issues we have in the world, but in the UK, is the idea of carbon capture storage. That we maybe take CO2 from industrial plants and put it down underneath the subsurface. And in the UK, the idea is going to go offshore into some of the depleted oil and gas fields. Now, what this is here is that a group of petroleum geoscientists were given a hypothetical set of information about a possible CCS site. And they had to evaluate the confidence they had as a good CCS site in relation to the reservoir, in other words, the rock that we're going to put it into, the seal, the rock that was going to stop the CO2 from escaping, and then a possible fault, a weakness that might let the gas escape over the long term. They got asked to make a judgment on their confidence about this a few weeks before a meeting, right at the start of the meeting, during the meeting, and then after the meeting. And what we see here is the level of confidence they have amongst the group. And what you'll see is, even before the meeting, they've got a range of values. So they're all looking at the same material, and they're coming up with different numbers. So already there's an element of subjectivity there. Why wouldn't they all come up with the same value? Well, because they're all thinking about things in a slightly different way. The interesting thing is, when they go to the start of the meeting, it's a slightly shifty range, slightly broader. Why? Nothing factual has changed. It's the same amount of information. They're making a slightly different judgment on a different day. They go into the meeting, they have a discussion, and then they have an even broader set of range. So in amongst them talking to themselves, some have started to get less confident, some have started to get more confident. And then finally, when they come back out, they make another judgment. And here is the same graph for the thing about the seal, how well it is. You see there's a shift here, there's a shift here. And then someone will get a little bit more confident as they go through that meeting. The really interesting one is when you look at the fault. Look at the fault. They've made a range, they're not very confident. Just before the meeting, they're a lot more confident. What is going on? In the meeting, they're really confident. And when they come back out, oh, they're not so confident anymore. No new data. Inherently subjective. The way we relate to each other, the way we relate to data, means that at different times we will choose different values on the basis of the same objective science. So I suspect this is in all sciences, but in geoscience, it's clear that our interpretation is really important. The other thing is that geology is a historical science, and it's lumped in. These are all historical sciences. Human history and archaeology, paleontology, the history of life, geology, the history of planet, cosmology, the history of everything. So time runs backwards from today all the way through to the Big Bang. And that means that, that's really important because what it means is that there's this part of the story of how things evolve. But it means that the events of geology way back in the past are unique. They will never happen again. And that's fascinating, but it's problematic for us. So this is a quote from someone who's talking about using geoscience for teaching sustainability, and he says, this combination of historical and interpretation science means that we really can inform society because it allows us to recognize the varying manifestations of phenomena at different spatial and temporal scales. So we can jump time scales and we can jump spatial scales, and that, therefore, our science is really useful for that. Because sustainable processes that underpin sustainability also will kind of jump around. I said about time, and this quote from geological, it should be Eldridge Moore, I don't know why it came out like that, is really interesting because he talks about our relationship with time being, in a geologist's brain, it's slightly schizophrenic view of time. That in the same way, we can balance two very different concepts of time. One of them is the human and emotional, and the other is the geologic. And he goes into the geologic one as these slow rate of geological processes, centimeters per year, huge effects have continued for enough years. 1 million years, it's a small number on the geological timescale, but in human experience, completely fleeting. And the notion that for much of our time, our interests are way in hundreds of millions of years ago, it's always been one of the reasons why geologists have been kept away from many of the contemporary issues. But actually, of course, we are, for a start, humans, and therefore we've got a human and emotional interest in what is happening absolutely now. The way I kind of think of this, got a railway track up there, the way I kind of think of this is that geology is when you're at a little provincial railway station and the intercity train is approaching. And when it turns the bend, you can see it's a train, you can see how many carriages there are, and you can see its colour and all the rest of it. You can't see any other detail. And that's geology. Looking in the past, we've got it's a far away, distant one. We kind of lack the detail, but we can see the general picture of what's going on. And then that train comes whizzing through the station, and it's just a cacophony of noise. It's a blur. You can see images, hints of people in there. You can see some writing on the train, but you can't take in the data. You're kind of overwhelmed by the sheer magnitude of information that your brain is receiving. And I think that's the kind of distinction I'd make between the way geologists look at the planet, with that very kind of generalized view, and those that are working with contemporary data sets, which we've got this huge amount of data. So geologists have this ability to kind of step back from it and see it in perspective. So the key thing is that geology is this derivative science, which has always been used to bring it down, to say you're not really a proper science. This is what the editor of Nature, Henry G., said, talking about geology. It can never be truly tested by experiments, so they're unscientific. And it's true. We don't have rules, or laws, rather. We have rules of thumb, things that work for us, and that we use other scientific disciplines, maths, physics, chemistry. We use it very loosely to apply to the workings of the earth, and we pick and choose what we apply to. We can't do experiments, or we can't do we can do experiments, but we can't do experimental control about what killed the dinosaurs. You can't run that thing. It's too complicated, for example. So we're not an experimental science. Can't go back into the lab and think, oh, let's just try to change this. We've got essentially an incomplete data set. We always deal with an incomplete data set. You just need to go around to see how many times rocks stick out of the ground. Outside of the Himalaya, not much. And even when you have a sequence of rocks, most of the time is missing from that sequence of rocks. And then also this last one I've talked about, time is most of the processes we look at are so slow that direct observation doesn't really help us. All of these are seen as deficiencies and weaknesses. And that may be true in relation to some of the higher sciences. But in terms of sustainability, many of these things apply. We can't do experimental controls because there's too many variables. We're often lacking the real critical data. The processes are going too slow to really see the fundamental ones. It means that geologists should be really perfectly placed to switch some of their attention to many of these issues. The third point I'll introduce by way of another little clip, and I'll come back to it at the end.
Our planet has immense power. And for most of human history, it has dominated us. In the series so far, we've seen how the forces of the planet, the deep earth, wind, fire, and water have all had major impacts on human history. But now the relationship between us and the planet is changing. We're no longer at its mercy. We have now become a major planetary force.
The fundamental elements of our planet have helped shape human history. But now, we ourselves are a force of nature to be reckoned with. Even in the wildest corners of the earth, we can't escape our human influence. The question is, what does that mean for our future?
So this notion of a human planet has emerged really in the last few years with the recognition that humans are a geological force in many different aspects. We shift more soil and rock through bulldozers than rivers move across the planet. We can chemically change now any part of the atmosphere or the oceans. Short of a cosmic impact, we act on the planet faster and more effectively than any natural process. And geologists are now arguing about when that really impact kicks in. And to some extent, it doesn't really matter. What we know is that certainly by the latter part of the 20th century, we are working dramatically on it. So this is, obviously the graphs are too small to see, but this is 1750 through to 2010. And this is socioeconomic things, so that's world population, GDP, so that foreign direct investment, urban population, large dams, transportation. What you see is this line here, the red bit here, and the line is 1950. So post-war economic boom across the world throws the world into this frenzy of industrialization, globalization. And these are the equivalent things in the Earth systems to do with carbon dioxide, methane, temperature, everything else. So suddenly the planet's gone into overdrive in that it's affecting the planet. So for a long time, humans and geology was separate because we were studying things 100 million years ago. Humans were never there. Now the Anthropocene, as it's called, means geologists are now working right here in the last few 1,000 years and 100 years. So this has changed completely the dynamic. So this quote from an environmentalist, Thomas Barry, says, "We're at the present participating in an unparalleled change in the human-Earth situation. The planet that ruled itself directly over the past millennia is now determining its future largely through human decision. We are in charge, basically, of what the planet does and life on the planet." And that's an extraordinary responsibility. So this takes me to that general point I started with, which is the geologist. What's its role? Do you trust the planet with a geologist, or is the geologist the problem? Now, actually, that reflects, of course, society. Geologists just do what they're told. If they're told to go and find stuff, we'll go and find stuff. If we're told that we don't want to go and find stuff, that actually this is an important thing, we'll study that. But as you are a young geologist coming through, where you lie is really a continuum between understanding the Earth economy and feeding the human economy. And you will place yourself at different places. Many of you, some of you might want to be rich and earn lots of money. If you want, then that's the place for you. Some of you may not want to be rich, but you might want to have the richness of the knowing that you're helping the planet, and you'll be somewhere up there. Most of us are somewhere in the middle with bits of both. But it is this point that actually geoscientists are starting to be able to define where they are. And now this next clip just kind of illustrates the problem, the paradox, I think, that we're in.
If you want to get a sense of a changing relationship with the planet, then this vast expanse of mud is the place to come.
This is no ordinary mud. The towering column of steam shows that this mud is emerging from within the Earth at boiling point. I'm in Indonesia, one of the most volcanically active countries on Earth, which is a clue to the origin of this strange phenomenon.
You know, what's happening down there is one of the most unusual eruptions on Earth. It's a volcano, but it's not spewing out molten lava. That is a mud volcano.
This volcano began erupting in 2006, and for the people who live here, it's been a disaster. Around 30,000 people have been displaced by the mud flow, and around 10,000 homes have been destroyed.
You know, the scale of this is truly enormous. And all the way around it's surrounded by villages that are kind of, many of them half flooded with the mud. Like that there. Look at that. Completely buried these trees here.
Down on the ground, there's a real sense of desolation.
You know, up close, it's the sheer oddness of the scene that strikes you most. Like the fact that I'm walking alongside the roof of a mosque. A mosque that was once the centerpiece of a village that now lies entombed in solid mud beneath me. Such an eerie feeling.
It's as if the planet has decided to reclaim this place from humanity. Life has been completely smothered. But there's something that makes this eruption unique. And that's what it was caused by.
The eruption has gone on out there is really special because it's almost certain it's not natural at all. Geologists think that it was triggered by us, by human activities, when an underground probe for natural gas went horribly wrong.
In 2006, developers were drilling in search of gas, but at around 3,000 meters, they withdrew the drill. The pressure in the well then dropped, which sucked in hot water from surrounding rock. This caused fractures in the rock. Water burst through and shot upwards, mixing with layers of mudstone to form a liquid mud that boiled to the surface. Every day, enough mud emerges to fill more than 40 Olympic-sized swimming pools. To try to contain the flow, enormous levees have been constructed. Wallowing machines are still trying to channel mud away from the surrounding villages. Concrete blocks have even been thrown into the center of the volcano in an attempt to plug it. But every effort to hold back this relentless tide has failed.
To me, this eruption symbolizes a strange relationship with the planet today. On the one hand, we are an incredibly powerful force now, capable of triggering volcanic eruptions. But on the other hand, we're not really in control of that power. Much of the effect that we have on the planet even takes us by surprise.
So that's the rub, really, is that we're now in a position to influence the planet in ways that was previously determined by some of its major forces. And that means that along with the kind of the skills of being a geoscience, one of the other things is the responsibility and the ethics about what we want to do. And this idea of geoethics is something that's now come to the fore, which is that we have a responsibility to think about the stuff that we're doing, and that's making geologists question their role about that kind of continuum about Earth steward to Earth, if you like, exploiter. So just to go back then, I think that all of these issues, all of these issues have this in it. All of these issues have the two sides. All of these issues bring with it an influence on society and therefore a responsibility to do the good for society in these areas. And I don't have time to go through them all, and I've not really got experience in all of them, but I'm going to talk about hazards because I'm an earthquake geologist and that's what I know. I'm going to particularly talk about Istanbul because I've been working there off and on for the last 10 years, and I've got a big project there at the moment. And this is an earthquake that happened just to the east of Istanbul in 1999, killed about 30,000 people. You can see the pancaking of the apartment block, something that's just all too familiar in many, many different earthquakes. And Istanbul is a city that has had earthquakes for thousands of years. And it's been populated for thousands of years, so we have chronicles of it. But we also see it in the buildings. This is an ancient mosque that's basically got all these stone buttresses around it, holding it up, because it's been damaged by earthquakes ever since it was built, something around 600 AD. So the buildings, the ancient buildings, know that this is a city that gets earthquakes. But what about all of that? Istanbul hasn't had a direct seismic hit in 250 years. And in that time, it's grown from a city of a few hundred thousand into a city of 13.5 million people. What we're worried about is the rupture of something called the Prince's Island segment, which is just offshore. And that is the only significant section of a 400-kilometer long plate boundary fault line called the North Anatolian Fault, all of which has ruptured in the last 100 years, except for one section, and that is that section there. Oops. And, of course, just 10 miles away, 20 kilometers away, is a megacity. So the science that's gone into that, the geological science, is really complicated. But actually, what is really super complicated is what do you do about it? What do you do about for a city where I would say, and there's a lot of young people in here, but I would say in your lifetime you will see Istanbul struck by a major earthquake. Now that is okay to say that, but what do you do about it? How do earthquake scientists contribute to the safety of the people in Istanbul? That's what I'm interested in. The earthquakes in 1999 demonstrated the vulnerability in that area, such that there's lots of different estimates, but the estimates are that a magnitude 7.5 earthquake will destroy 50,000 buildings, and maybe 30 to 40% of the building stock isn't up to a large earthquake. The population, the people there, know there's going to be an earthquake. If you go into the streets and you ask them, they say, it's going to be an earthquake, isn't it? You go, yeah. They go, it's going to be big, isn't it? They go, yeah. They know. But actually, if you look at what adjustments or normal people in the Istanbulites have made, it's very hard to find it. They're not making any adjustments to their seismic safety in terms of personal safety, having emergency plans, emergency kit, knowing what to do, knowing where areas are to go, making sure their buildings are as secure as they can be. This map of Istanbul shows that in orange, the areas where the Japanese scientists came in and did a micro-seismic zonation map to demonstrate the areas that have got heightened seismic shaking potential and liquefaction potential. So these are high-risk areas. And then the government, the city government, identified in red other areas of high seismic risk, largely through loss of potential cultural heritage. Now, so my interest, really, I'm not a seismic, I know many of you will be earthquake engineers. My one's not the buildings, but my one's people. So I'm interested in what these people think. And to understand the next bit, you have to go into understanding the psyche of the people that are living in this area. Now, this is a study that's been done by psychologists, cognitive psychologists in UCL in London, comparing what people think in Western USA, Turkey, and Japan about earthquakes. And what I really want to draw out is the difference that Turkey has to those other two countries. We could talk about the whole thing about California, we could talk about Japan. I'm just interested in Turkey. So Turkey's in red. So fatalism, they all have a high degree of fatalism. Fatalism means, you know what, it will happen. It's going to happen. So they all have a high level of awareness. They all know you get earthquakes, so that's not a surprise. There's a bit of disagreement about how much control individuals think they have, but look at this one. Very high level of people in Turkey would say it's an act of God, some kind of divine retribution. But more practically, someone that says, how presumptuous of you scientists to say about when there'll be an earthquake. God will decide when there's been an earthquake. In fact, God will decide if I'll ever die in an earthquake. A lower part arguing for acts of nature, but again, another one that's heightened. Acts of people. It's not saying that people cause earthquakes. What it's saying is that the disasters that result from earthquakes caused by people. And to unpack that a little bit, I want to look at this in a bit more detail. So this is the same thing. Turkey's still red. And what have we got here? This is some of the factors that are underlying this. High levels of worry, anxiety, and fear in all three places. They have all been demonstrated, recent earthquakes, that they can kill people, so people are worried. But especially level of despondency, despair, sadness in Turkey. I'll come back to this one. The other one, the heightened one, very high sense of vulnerability, much higher than the other two, because in 1999, they saw neighborhoods identical to theirs, just 50 miles away, crumble. So there's no getting away from it. They know they're in the danger zone. The other thing, though, that sets it apart are these ones. A demise of identity, a sense that Turkey is losing its moral fiber, that it's going downhill. Turkey is a country, it's the East and West kind of transition. It's been a secular society that's becoming religious. It's a situation in turmoil. And so part of this is a sense that the country is going downhill, which kind of feeds in a little bit to this idea here. The reasons for this is a high level of expectation of corruption that is endemic in the system. That big business is in the driving seat. That the state isn't doing what it should do, largely because it's in cahoots with big business and the whole system's corrupt. Huge amount of distrust and a really significant amount of anger compared to anything else. So the point here, I guess, is to say, well, hold on a minute. This isn't geology. This isn't rocks and stuff. What are the... And it's not. This is psychology, sociology, anthropology. But here's the thing. Me, as an earthquake scientist, when I start to tell people about earthquakes, this is the environment, the common environment that I'm talking to. In other words, one of the ironies that we have in communication is we often get the basic scientific message across quite clearly. Everyone in Istanbul knows there's going to be an earthquake. But one of the ironies of that is that message, being so clear, gets kind of taken into the normal discourses of city life. What people are normally worried about. They're normally worried about their jobs and their health and the government and all the rest of it. And earthquakes just become part of that complex process. I always thought that if I said that I'd done a study that said that the earthquake was going to be bigger or more frequent or something, that was going to be fantastic. It's going to be great for telling people about science. But now I realize that information is probably going to get taken in and used in this big, complicated social, cultural thing that I've got no control over. So what is my responsibility as a scientist? Because the environment, the people that I'm trying to talk to, that's what they're worried about. And if I just talk about geology, then I'm not connecting with them. So I want to just report about, because I'm interested in how we get all of this into geology. So I've got a project with the EU, and we're taking normal geologists. This is a tectonics person, and this is a geophysicist, and these are all various geology PhD and postdoc students. And we take them on a field trip to the inner city Istanbul with an urban historian, where we meet local residents. And again, for those who say, well, it's a very strange field trip, it is a very strange field trip because it's got an anthropologist in there. This is my PhD student, Johanna. And we're interested in trying to confront the students with the reality. So they see seismic risk from a theoretical, practical point of view of the classroom. Let's take them into the actual districts, let them meet people and see how real people think about seismic risk. And the story in Istanbul is very complicated. I normally have a whole lecture on it. But essentially, you start about in the 1920s, 1930s with people coming in from Anatolia, building very simple settlements on the edge of Istanbul, where they are a labor force in the factories. And those ghettos grow bigger and bigger and bigger until they become a really sizable set of illegal housing estates around Istanbul. So sizable that in 1984, the government has an amnesty and says, look, you're illegal, but we now make it illegal. We cannot knock down your house. And at that point, the people build their little shacks into concrete and brick, and they normally have one story, and then some more family comes from Anatolia, and they build a second story, and some more family come to Anatolia, and they build another one. And they end up building large blocks. But the point is, those constructions have never seen an architect, never seen a planner, never seen an engineer. They're built by one guy and his brother and his uncle going, collecting materials and putting it together. So they will fall down in a relatively minor earthquake. Then what happens with a free market enterprise is that an entrepreneur comes along and says, hey, you own that. I tell you what, we'll knock it down and I'll build you a nice building. You can have the 2/3 of it and I'll take 1/3 and I'll rent it out and we'll make some money. So you get these houses that are nicer. You know what? That guy, that entrepreneur, he's not an architect or a planner or an engineer. He just builds it in the exact same way as that, but he makes it look nice. So that will fall down during an earthquake. Then comes 1999. Lots of buildings fall down, and people suddenly realize the problem. So now what's going on is a big process called urban renewal, whereby in these districts, they're building these high blocks. Now, these blocks are supposed to withstand earthquakes, and that's what everyone is kind of told. And the important thing here is that if they do withstand earthquakes, they're clearly better than all of these. Agreed? Makes more sense. They withstand it, that's good. However, these buildings aren't financed by the city in public money. They're financed by private finance. In other words, big business. And so they need money back. So only about 30% of the maximum of the people who were living in these ones go in there, because most of them can't afford the rent. Many of these other ones are sold off for high rental values. So a lot more people come in. The original community gets fragmented. And this is the key thing. More buildings are put closer together and more people are put in. So the actual human density has gone up in the highest risk areas. So more people are being put into the areas that we already know have got high risk. And the only way that that is possible is because that's a financing situation. So here we have that area was in Brno, which is located down here. And this is Orhan Essen, the social scientist, is saying it's a market-driven risk mitigation. But to make it work, you have to increase density. Financing is through the market, not public funding. The increase in density is in clear contradiction to the requirements of the earthquake code. In other words, we know this area is dangerous for earthquakes, but we're putting more people into it rather than less. And we're justifying it by saying that, you know what, these new buildings will stand up to earthquakes. And he has said that. He lives here. He lives now in one of these fancy new buildings from what was out, well, it probably wasn't that, was one of these ones before. And he's quite positive. He says, you know, this used to be a football field. Then there was this urban transformation process, so people have been taken to these new buildings that are safer for earthquakes. So the key thing is, if these stand up to the next earthquake, then by and large, this will be a good thing. But of course, these buildings are built for relatively low-income families. So you have to trust the little bit of paper that you're given that's been signed off by an engineer that says that building was built to withstand earthquakes. And of course, the acid test will be the earthquake to decide that. Other areas, it's even more contentious. This is Okmedani, which is a district where, again, it's an immigrant area from Anatolian villages, very low-income families, quite high crime rate neighborhoods. People in there are very skeptical. This is about how much information they're given, because the government's coming in and knocking down many of the buildings, and in the name of seismic hazard. He says we're not informed at all. We believe the earthquake is just used as an alibi, as an excuse, as a pretext. The term earthquake doesn't really point to the real thing. The real thing is they just want to acquire this very precious land. This interchange in here is the last major interchange in Istanbul. It doesn't have luxury malls and luxury apartments, because it's got beautiful views down to historic Istanbul, the Golden Horn. So what he's arguing, he says, in 1999, not a single building in my district had a crack in it, even though 3,000 people died in Istanbul and many houses came down. So he's saying, this is perfectly safe. Nothing to do with the earthquake. It's all to do with property prices and all the rest of it. Now, again, none of this has got to do with geology. But if I'm an earthquake geologist and I want to communicate my hazard, this is the kind of issues that we're dealing with. So we confront the students with these issues. So here they're talking to Ali, and one of the students says, what would change if we, scientists, went in and we demonstrated through seismic zonation and geophysics and stuff like that, that there was a high-risk area? And Ali says, first of all, we'd thank you, because we finally learned about the threat. we would then cooperate with you. We'd like to hear what you would suggest, because for all of us, human life is the most important thing. Please come to us with your suggestion, and let's think about what can be done. They've been asking for geoscientists to go and talk to them about why it's seismic risk. They've had very little response. In other words, geoscientists aren't really talking to the public, but they're key. Oh, what happened there? Stay. Good boy. I think it's a screen because my computer's fine. This is going to make you go into some kind of epileptic fit thing, so I have to be careful. So this is the students trying to discuss their responsibility. So I have to point this out and move it. Then what is your Any idea why that's happening? It's not a big deal. Essentially what these students have said is, the first one's saying, what is my responsibility? You know, if people aren't reached by standard geoscience communication, then what is my role? Have I really got to go in there and tell them to kind of move on? In which case, this last little bit, I'm already an activist. I've kind of stopped being a scientist. I'm now an activist. This one here says, you know, you're looking at the human aspect, not the scientific aspect. So the second one says, all that stuff's human. We are scientists. And we should be doing the science, putting the science out there, and then we step back. And then this first research says, I absolutely don't feel like that. You know, there's a scientific bit, but there's that human emotional bit, and basically I want to do something. And then this one says, well, you can make sure you inform the public better and find a way to around this corrupt system so that people are informed. And the last one says, yeah, but this is really complicated. And that's absolutely true. It's really complicated. So we're going to go into this one and see if it's done. That's better. This is the last slide. And the reason why I'm putting these up is because these are debates and discussions that I think all geoscientists should be having about all of these different aspects. The discussion here is, how do we communicate? And there's two kind of options, really. This researcher 10 is a bit despondent about all this. And he says, well, basically, our responsibility is to produce science, and other scientists can talk to people. And to use other scientists who can talk to people. So he suggests we want to bring in social scientists. We want to bring in anthropologists, sociologists, philosophy, psychology, that kind of stuff. We need people that can communicate this on. We cannot communicate directly. We need a translator. And then this other student says, or we could do it ourselves. In other words, or we're actually smart enough to grab hold of what's important in that and just incorporate it into geoscience. And then the last one says, yeah, but it's not going to be easy. And again, I agree, it's not going to be easy. And these are discussions that we're having about how do we effectively take our science to the public. Can we do it all by ourselves? We've not been very effective so far. Or do we need to bring in help from other disciplines? Or do we hand it over to those other disciplines and say, you go off and do it for us because we can? So I'm just going to finish then with some thoughts, just a bit of time, nearly, about how to do this and what the importance. So my point is that hazards one is a miniature version of all the others. If you went to all those other things about mining and oil and gas and climate and water, you'd find those same debates about a disconnect between science and the public, and how do we get our science across to the public. So this is from the Geological Survey of India, and one of the key things about the science strategy, just in the last 2 words, that it needs to be broad and multidisciplinary. So, in other words, it's bigger than what we've been doing before. We need to engage with other people, and I think that's right. And again, I gave you this quote earlier from the Geological Survey of India, and it says, you know, that geology is key to sustainable development. But the next words, it goes on to say what needs to be done. It says, to have an understanding of the Earth system, fundamental research in the fields of petrology, geochronology, and isotope geology, neotectonics, seismotectonics, paleontology, stratigraphy, remote sensor, and extinction. I kind of disagree with that, because actually that's what we already do. What this statement is saying is what we need to do is more of what we're doing now. And actually, I would argue what we've done now has not been very effective at getting our stuff across to the public, and particularly getting ourselves across to sustainability and sustainable science. So I think we need to be more ambitious and more broad than just simply studying more of what we do right now. these are the 17 sustainable goals that has been put forward. And actually, if you look at those, and you think, if you're a geoscientist or a geologist, you look at how many of them do I learn about in geology? Not many. I mean, maybe life on land, maybe climate. Industrial things, maybe. I mean, some things you could see indirectly. Hazards, for example, fits into sustainable cities. What I'm getting at is that geology is several steps away from what people have decided are the key issues for society. So here's geologists saying we're integral, we're critical for sustainable development, and here's what the world is saying sustainable development means, and there's a disconnect, fundamental disconnect between the two. So this is the reason why we're not represented. Despite all our advantage for geological reasoning, geologists are not participants in those discussions because we've kind of marginalized ourselves, really, in my view. So how do we do it? Well, if we're interested in getting geoscience into sustainability, it seems to be pretty obvious we need to get sustainability into geoscience. So when we're teaching about geology, we need to, in amongst that, be teaching you about sustainability. And really what that talks about there is if we get it into the geological curriculum in some manner, then what emerges is a new generations of professionals, that's you guys, well-versed in understanding and addressing many of these contentious issues. It makes you more relevant to the challenges that are coming. This is too long a quote, really, but it also says, this quote basically says, the other thing it might be is it might make geology more interesting or more relevant. In other words, more people might want to study it because they think, actually, this is a really important thing. So we might actually have a more sustainable curriculum. In the UK, geology is super popular right now, but I don't know what it's like in other countries. Other countries I go to, geology is kind of suffering a little bit. And the other thing, and the reason why I say I disagree with the Geological Survey of India report, it's funny, I'm going there on Monday, so that'll be interesting when I say this, is that, you know, this business geologists not engaged in these discussions despite all these skills because of all its complexity, and it requires innovative approaches and solutions involving multiple disciplines. And here's the thing, in the technological, natural, and social sciences, we geologists should be that holistic center that's bringing all those ones together, because it's only by all of them together that we really can do it. And so, this is my view of Earth science, which is kind of different to most places. So, for example, what we see is it's the Earth with all the things. So we're up there very familiar, material science, mineralogy, physics, chemistry all the way down here, kind of more biotechnology, biology. So you know what, we fuse, we merge with those ones pretty easily. There's a lot of geophysics, geochemistry, biology. We're kind of commonplace linkages. Then down this way, you've got environmental science, marine science, geography. We kind of have relationships with those. That's not that surprising. But what about over here? Human geography, archaeology, anthropology, philosophy, neuroscience, cognition, psychology. Actually, most of my PhD students now are in this sector. I've got a PhD student with anthropology, with psychology, two with human geography. And then the other area, which really we haven't touched at all, is up here. Health, political science, law, economics. Don't really have much to do with many of those. And yet all of those together are fundamentally about feed into sustainability. Now the question of how we do that is a massive one. We can't just pick up the geology curriculum, throw it out the window and start teaching all of that, because it's impossible. So how we move to that is difficult. What I would suggest, and the way I'm now director of this Sustainable Earth Institute, where I'm getting forced to decide how to do this, is my view would be that in first year, introductory year, we would have a module about geology and society. And we'd tell you how geology fits with some of this stuff in engaging about some of these big issues. And then you'd do all your normal stuff, you'd learn to be a geologist, and maybe at the end, the advanced ones, or maybe it's more of a master's, would then say, right, how does your geology that you've learned fit into some of these key kind of issues about society? But it's not going to be easy. Geology is quite a traditional subject. And how we kind of change that over is a big challenge to us. So I'm just going to finish there. that I think the challenges of a sustainable Earth are huge, but I want to see geologists at the center of it and not at the margins, and I think that means we're going to have to change the way we teach it. Thank you very much.
Any questions?
Are you shy? You don't look like a shy lot, I have to say, in a good way. How do we do it? I'm here to steal ideas and take them back to the UK and change my course. I mean, first of all, maybe some people disagree. Maybe because we lose things with that. Maybe we don't need to change. Maybe we should just keep going. But you know, in India, it seems to me that you are at the sharp edge of a lot of these issues. And you have amazing geology departments, and you have amazing geology. So I'm interested in whether you think it's something that is necessary or whether you don't. You know, maybe it's a perspective that we have all the way from kind of London. Silence. Oh, there's one down here.
Yeah.
Mud volcano over there. So we're only in the top 2-3 kilometers. So the subduction zone is in that place maybe 50 to 100 kilometers. Well, it must be more than that because you get the volcanoes. So it must be 150 kilometers down. Okay. Right. Mud volcano started in 1980. Yeah, actually, no, in 1990. I was working around in 2000, so 10 years afterwards. Yeah. No, it's not I mean, the high pressurized mud is undoubtedly part of that system, if you like, and there are natural mud volcanoes. Essentially what we did, or the oil and gas company did, was puncture a natural high-pressured mud system, and it came out. So it was an induced one? It was an induced one. Oh, right, yeah.
If there are no more questions now.
Any other questions?
Any other
before
questions?
we go? Oh, one at the back.
Yeah, please.
Here we go. There we go, Sal. Yeah. Doing it with a? So how did you integrate it? Means you just converting the ideas from geologist to the engineer, and that is the thinking phase, not the application phase. Right. So actually it's not a sustainable development from what I see. What's not sustainable? Sorry, I missed the middle bit. What do you think? Do you mean that what I'm suggesting isn't sustainable, or? Yes, no, absolutely. So what I'm saying is that the reason that geologists are not included in many of the discussions about sustainability is the problem of the blame lies with the geologists, not with everyone else not inviting us to the party. It's because largely what we study, we have is separate from the issues to sustainability. But we also then, when there are issues about mining and energy and hazards, we often complain because no one has talked to a geologist. And I think that the reason for that is that when we study the geology and we teach geology, we don't explain the bigger concepts that we have that in, that we're just one part of a whole set of disciplines. And it seems to me that if we taught it in a more holistic way, then geology would naturally be the very center of sustainability. And that although we don't deal with everything, again, we wouldn't necessarily be dealing with all of those sustainable development goals, but many of those goals would be more central to what we talk about. We might, for example, set up a mining and economic geology course or a mining geology course, not as this is how you get the stuff out of the ground, but this is how we get it out sustainably and how much do we need, and it's just a case sometimes of changing the framing of the things that we teach. We still need to teach the basic geological skills. People still have to be able to leave as a working professional geologist. So it's more of a mindset change, I think, rather than a fundamental change. But you're absolutely right. I don't know many places in the world where this has been done. So it's very much a theoretical. But I see it as setting the framework for how geoscience is going to contribute in maybe 10 years, 5 years, not right now. Thank you. Yes? Yep. It's a good point. If they all suddenly, we got through to them tomorrow and they all realized, what would they do? Where would they go? I mean, there are things they can do, but equally, if it's a really big earthquake, then it's limited. I think, and it is a bit of a cheat putting up Istanbul, because actually I'm not sure that there's much that we can achieve at that one. I see the Istanbul example as changing the way we approach it. What I think is one of the keys, and we don't do enough of in science and in geoscience, is actually go and meet the people who are going to be affected by the things that we study. We study these things in theoretical ways. We don't go and look into the communities that are affected and ask people what they're interested in about. Instead, what happens in Istanbul is if you ask the earthquake engineer or the earthquake geologist, they say, look, we don't talk to the people because the people are stupid, they're uneducated, and they don't know. So it's pointless talking to the people. What we do is we talk to the politicians who are in charge of the local authorities, civic authorities, planning laws. And we talk maybe to the journalists because they can reach lots of people. But in any society, if you ask them who they trust least, it will be journalists and politicians. So scientists are not talking to the public and giving their information to the two sets of people that are least trusted. Scientists, by contrast, are trusted. And I think that what we see is when we go in and we meet people, you can have a very personal, honest relationship with people who ask you honest questions, and you can honestly turn around and say, we don't know that, or we do know this. So I think part of the change that I'm talking about here is scientists talking directly to those people that are going to be affected, that literally are going to die, rather than going through a system that is seen skeptically, suspiciously by most people. So it's changing our mindset as scientists as much as trying to change the public. I don't really think we can change the public in the short term. But I think over the course of a few years, we can change the way that we approach the public. And that's coming in. In the UK now and in America for a while, scientists are getting encouraged to go and speak to the public. I think it's coming in India. There's more information on outreach and going in and telling people. But again, that will be a slow process. But you're right. I mean, suddenly if all the people in Istanbul learned all of that seismic information tomorrow, the earthquake would still come and many of them would still die. So it's not a solution to saving hundreds of lives. It's just about changing our relationship with the people that matter.
I request Professor Sandeep Singh to present a memento to today's speaker.
Shall I stay here? Or?
Yeah, please.
Oh my gosh. Thank you very much. It's a pleasure. Look at that. Thank you. That was wonderful. Thank you.
I request Professor Sandeep Singh, today's chief guest, to address the audience.
Thank you, Ian, for such a stimulating talk and bringing other sciences as well into the geosciences. Because the way we see the geoscience from the quantitative analysis to the qualitative analysis, it has changed over time. Now, with the new input from other sciences as well, and we thought that as a geologist, our duty is to bring the basic data, what is required for any development, for infrastructural development, or even developing certain structures, or for that matter, even looking at these earthquakes, tsunamis, to bring the basic data to the engineers so that they can consider those aspects during their design. And with the advent of more and more sophistication into the instrumentation, I think we are advancing towards that, but still, as you said, that we need to go to the public as well for sensitizing them about the problems which they might have is a good idea. And with this, I think it was a good talk to all of us, but still we require to have the basic geology going. Thank you.
Thank you, Professor Singh. Now it is a time for vote of thanks. I request Professor D.S. Arya, Head of the Department of Hydrology, to deliver vote of thanks.
In the end, I would like to thank the organization and person who helped us in organizing this lecture. And first of all, I express my gratitude and would like to thank you, Professor Iain Stewart, who agreed to visit IIT Roorkee and to speak about towards a sustainable Earth. I'm very sure that the faculty, staff, research scholar, and student might have enjoyed this lecture. I'm very thankful to the chief guest of the function, Professor Sandeep Singh, Dean Alumni Affairs and International Relations, who was very instrumental in organizing this lecture under the lecture series. I'm also thankful to the chief guest because he spared his valuable time and joined us here at this time. So thank you very much. I'm thankful to the British Council, IISER Pune, and Dean Srick, IIT Roorkee for supporting and cooperating in this organization of this lecture. I'm thankful to all the students, faculty, staff who are here and have attended this lecture. Thank you very much for joining us. And I would like to mention one more name here. It is Dr. Anil Gauri Shetty. Right from the day one when I proposed him that this lecture is to be arranged, he took all initiatives and responsibility of arranging the lecture. So thank you very much, Dr. Gauri Shetty. Once again, thank you very much and have a nice evening.